So building on our understanding of enzyme control, we're going to study one enzyme that's part of sort of a metabolic system, or what we call a substrate cycle. We're going to discuss sort of glucose homeostasis from a top-down and bottom-up approach. So here's what we mean here. I'm actually going to have a story that I'm going to split into sort of two pieces here. So I'm going to split my page in half here. Okay, so when I talk about sort of maintaining glucose homeostasis, so that's maintaining, and I can't spell glucose right now, glucose at that important 5 millimolar level. Again, if we're having low blood sugar levels, we can remedy this by what we call a top-down or bottom-up approaches. So here's the top-down approach, is we're going to take glycogen and we're going to break it down. So this is what we call our top-down approach, and this is glycogen breakdown. We also can have what we call a bottom-up approach. And that's going to be taking non-carbohydrate precursors and converting them through a process called gluconeogenesis into glucose. That name literally means glucose from the beginning, glucose from scratch. Okay, so these are the two ways that we can think about remedying low blood sugar levels. So that's going to be a need state. Top down, we can break down glycogen, and our focus in this learning unit is going to be on studying the rate controlling enzyme for glycogen breakdown. And then there's also this other arm, this bottom up approach, which is using the chemistry of gluconeogenesis to make non-carbohydrate precursors into glucose. So as we think about sort of maintaining glucose homeostasis, really there is what we call a substrate cycle, which is the interconversion of glycogen to glucose and then back into glycogen. So one of the things that we'll sort of talk about is the important enzyme responsible for doing this breakdown piece is phosphorylase. So that's the enzyme responsible for breaking down glycogen into glucose. And then on the other arm of that is synthase. So we've seen these enzyme names before. Okay, so these are the two rate controlling enzymes. Again, it's not to say that there's only one enzymatic step, but this is the important rate controlling enzyme for converting glycogen into free glucose or glucose back into glycogen. And this is what we call a substrate cycle. And one of the things that we talked about in class is we would not want both of the arms of this pathway operating at the same time. So again, these are not both operating at the same time. This would create what we call a futile cycle. Okay? And again, a futile cycle is not only not desirable, but to highlight what a futile cycle means, it would be the forward and reverse processes both happening. Forward and reverse processes both happening. So let's just map on a little bit more about what we know or what might be happening sort of to have either one of these arms be operational. So if we map on what we might think about what is happening in these different states, if we are doing glycogen synthesis, okay, we are likely in a fed state where we have high levels of glucose that need to be made into glycogen. Conversely, we are going to be in a need state if we are having lots of phosphorylase activity, which are going to be taking glycogen reserves that we have in our liver and sort of breaking them down into free glucose. Okay, so mapping on, again, some other terms that we've learned about. So if we are fed state, that must be D-phospho. Okay, need state is phospho. And just a new set of terms that we really haven't talked about specifically yet, but they sort of apply with what we're going to see a lot here, is when we are in a need state and we are decorating things with lots of phosphate. So we're in that phospho state. Let's just map this on too. Let's use these terms. That means we're going to have a lot of kinase activity versus a lot of phosphatase activity. But the new terms that I wanted to make sure to map on and introduce is we are going to be in a catabolic state. We're going to be breaking things down versus an anabolic state. Okay? And so that's going to allow us to really sort of think about the kinds of arms that we want to have. And it doesn't make any sense to have a catabolic set of processes happening at the same time that an anabolic set of processes are happening. All we'd be doing is unnecessarily burning money, burning energy. Okay? Because catabolic processes tend to generate energy, anabolic processes tend to use energy. So again, we could even map those pieces on here. Let's find one more sort of color here. This is going to be fed state, is going to be actually putting that extra energy in. And then, I don't know if that makes sense with minus and plus. Let's see, we're going to say we're going to take energy, and this is going to generate energy or biological money. Okay, so the last thing just to kind of highlight here before we kind of look at this picture, which is really thinking about how this enzyme is controlled, how its enzyme activity is controlled. We're going to look at it from a structural standpoint. I want to make sure I'm going to move this here just to highlight how we think about this enzyme phosphorylase doing its chemistry. So let's think about the chemistry that we happen with phosphorylase. Okay, so here's the chemistry that happens with phosphorylase. So thinking about the linkages that we have. So remember, glycogen is a polymer of glucose that's linked with alpha-1,4 glycosidic bonds, okay, and then alpha-1,6 branch points. But the enzyme is actually going to be breaking these alpha-1,4 glycosidic bonds. So just like we learned about with breaking glycosidic bonds with lysozyme, okay, that was a hydrolysis reaction that broke that glycosidic bond and generated free glucose. Here's how this is similar but different. We're going to have glycogen. That's, let's say, N residues. Okay? We are going to be using not water, but we're going to be using inorganic phosphate. And that is going to be generating glycogen that has lost one of those residues. Okay? And then we're going to be generating glucose 1-phosphate. So let's draw that structure here, right? We know how to draw glucose. So this is going to be glucose 1-phosphate. So at the 1 position, there is going to be a phosphate group. So here's the rest of glucose. Okay. Okay, so glucose 1-phosphate is going to be taking this phosphate, and rather than this being an OH group, like if we had hydrolysis chemistry happening, it's generating glucose 1-phosphate. So this chemistry is called not hydrolysis, but phosphorylasis. And that's because we're using phosphate as a nucleophile and not water. Okay, so let's map on what this looks like in the enzyme active site. Okay, remember, we've got T state and R state to think about whether an enzyme is conducive to binding its substrate. So here we have T state, here we have R state. I'm using red to indicate T state is kind of a stopped state. It's not going to be doing chemistry. Green for R state, it is doing chemistry. But what that has to do with is R or T state means that we are in a shape that is not conducive to binding its substrate or doing chemistry on the substrate. So we have a shape that is not conducive to binding or doing chemistry on the substrate. Okay? And so whether it's T state or R state is determined by one specific structural thing in this enzyme. So T state versus R state, okay, is determined by the position of the N-terminus. And what does that mean? Well, let's highlight where the N-terminus is. So I'm going to use purple here for this. The position of the N-terminus. Okay? So here in the R state, we're going to say that this N-terminus is exposed. So when the N-terminus is exposed, that means we are in a shape that is R state, that is conducive to binding substrate and conducive then to doing chemistry. Here's where the N-terminus is in T state. Okay? We're going to define this as buried. So the position of that N-terminus is going to determine whether we are T state, not able to bind our substrate and do chemistry, or R state, able to bind our substrate and do chemistry. Okay? So R state, T state sort of comes into play here, but importantly, I'm going to zoom in here and we're going to highlight some important details that are happening when this N-terminus is exposed. So one of the things that we can see here is there's an important residue that we have right here. This residue right here is serine 14, and I do want you to remember that name, okay? Serine being something that can be added or removed phosphate, right? We can add or remove phosphate groups from a serine residue, okay? Kinases are going to add those phosphates. Phosphatases are going to remove them. But importantly, when we add that phosphate group, so here's that phosphate group, here's that phosphate right there. When we add that phosphate group, that introduces a negative charge. It takes that serine's hydroxyl group that was polar but neutral and now makes it negatively charged. And here's the key. When we would have that N-terminus now have that negative charge that's there, we do not want to bury that in the inside of an enzyme, right? That's where that hydrophobic core is. That's where it's very nonpolar. So it's very unfavorable to bury that N-terminus if it's phosphorylated. Here's another piece that we have here. Not only is it unfavorable to bury it, but look at this residue that we have here, okay? This residue that we have right here is an arginine. And I probably could have written it as an R, but I didn't want to get confused with R state. It's an arginine residue. Remember, arginine, the side chain is that guanidino side chain. That's positively charged. So when we create this negative charge by phosphorylating that serine residue, not only do we not want to bury it, so it wants to be exposed, but we can lock it in with interactions with this arginine residue here. So phosphorylation is going to lock us into an R state, which means we are conducive to binding and doing chemistry on our substrate. One last little piece to highlight here, if we look at this region right here, and I'm not going to go too much into the structural details as to why, but the site that I've highlighted here is what we call the allosteric effector site. Okay? The allosteric effector site is a site where we can bind a small molecule that's going to help modulate whether we are T state or R state. So one of the things that I want you to remember is we're going to learn about certain small molecules that tend to be fed state signals or need state signals. So I'm going to fill in these boxes either ATP or AMP. Okay? Logic check should allow us to explain which is going to go where. AMP is a need state signal. So it makes sense that AMP should bind to and stabilize R state in this enzyme that's responsible for breaking down glycogen and remedying that low blood sugar level, which is a need state. ATP is a fed state signal. So again, makes sense that a fed state signal would bind to and lock in the T state for an enzyme that's responsible for breaking down glycogen to make free glucose. We don't need that when we are in a fed state. So all of this should map and make sense in what we call a logic check, okay? But highlighting this is a key player in glucose homeostasis, and it's by kind of modulating what happens with glycogen breakdown or glycogen synthesis, that substrate cycle. Glycogen phosphorylase, such an important enzyme that we can even just call it by its last name, phosphorylase.